In Part 1 of Lecture 8, we will discuss memory basics. Computers could not work without memory. Programs are stored in memory. Data is stored in memory. While we can read a program from a disk and even store most of our data on disk, we need at least some memory if our programs are going to run with any decent speed. Memory can be viewed as a one-dimensional array that can be accessed directly by its unique numerical address. Memory can be an array of words or bytes, depending on whether addresses are assigned to individual words or bytes. A word is usually defined as the number of bits that the CPU will normally manipulate as a unit. Older computers were frequently word addressable. The norm for modern computers is to be byte addressable, which is much more flexible. This way, instructions can manipulate individual bytes or any aggregate of bytes that the designers of the instruction set decide to allow the user to manipulate at once. This kind of freedom is not available on word addressable computers. Executing an instruction requires the CPU to access memory several times. First of all, the CPU has to fetch the instruction. That's one memory access. Then it fetches the operands. That is one or more additional memory accesses, unless the operands are stored in registers. Lastly, whatever result is computed must also be stored. That's one more access, unless it's into a register. Memory allocated to one process is not normally used by another process. There are exceptions to the rule, cases where one process will share a portion of its memory with another. But this can only happen when the process permits it. This kind of memory sharing allows two processes to talk to each other, as we discussed earlier. Computer program instructions usually include addresses, either of operands or of the point in the program to which it will jump. These addresses rarely appear as physical addresses, the actual address that is used in loading and storing data. And this is done for good reason. There is no guarantee that a program will be loaded into the exact same location in memory each time. There are several reasons for this. If we are running a new version of the operating system, it will use more memory than the old version, so the space allotted for application programs may start at a higher address. If we allow more than one to be stored in memory at a time, the program may not always get the exact same memory allocation each time. In either case, if the program is not loaded into the same area of memory, then references to physical addresses would be incorrect. What we need is to devise some way of representing addresses that will be valid even if the program is loaded into different areas of memory each time it is used. People don't write programs in machine language these days, and haven't since the 1950s. The lowest level at which anybody programs is in assembly language, because it is too difficult to develop error-free programs when you're working exclusively in ones and zeros. Most programs are developed in higher level languages such as C++ and Java, or with programming tools such as Visual Basic. Since the computer cannot understand languages other than its own machine language, these have to be translated into machine language. The programs that create a translation that is saved is called a compiler. Compilers usually create files called object modules, program fragments that are not ready to execute. Not all the operands have firm addresses, because they may include data or procedures defined in other program modules, or they may include library procedures that have not yet been inserted into the program file. The process of combining all these modules into an executable module, a program that can actually run on the computer, is called linking. This also involves resolving any address information that has not been determined already. There are different points in the translation of a program where an address can be created. Addresses can be bound to a variable, or a variable's address can be set at compile time, load time, or execution time. Some programs are destined for a particular portion of memory. This is where they reside each and every time they are run. DOS programs with the COM extension fit in this category. Since they always occupy the same memory space, there is no reason to believe that a compiler cannot fix their address. Most programs, however, do not always get loaded into the same area of memory. Also, most programs are compiled and linked separately. For these reasons, addresses cannot be fixed before linking. Also, unlike our earlier case, we cannot use absolute addressing. We need a way of expressing an address that remains valid, even if the program is loaded in a different area of memory. We call such addresses relocatable, because the program can be relocated into another part of memory without making the addresses invalid. If the process is going to be moved from one memory segment to another during execution, setting the addresses has to be delayed until runtime. Dynamic loading offers more efficient use of memory. The only part of a program that is loaded initially is the main program. The other routines stay on disk until they are needed. When a procedure is called, it's read into memory, and the program's address table is updated. The advantage is that a large program only needs a fraction of its total memory requirements to run. The disadvantage is that the programs require a much larger number of disk operations to run, and these take up a lot of time. Dynamic loading programs can be designed and written by users, so there is no need for special support by the operating system. Static linking, the more conventional way of linking object modules and libraries to create an executable module, puts everything together in one file that is loaded at one time. Dynamic linking offers more efficient use of memory, linking the program with a small code fragment called a stub. Instead of calling the procedure, the stub is called, which then loads the necessary routines into memory, if they aren't already there, and then replaces its image with that of the procedure. Unlike dynamic loading, dynamic linking requires the support of the operating system. Another trick is the use of overlays, where a portion of the program is overwritten by another portion of the same program when this new portion is needed. We see in this slide a two-pass assembler as an example of a program using overlays, where the code for the first pass is replaced by the code for the second pass. Once the first pass is complete, its code is no longer needed. It can now be replaced by the code for the second pass. Any programs with modules that are mutually exclusive can take advantage of overlays, and overlays do not need special support from the operating system, only an overlay driver. But let the programmer beware. Programs using overlays must be properly designed, or they just won't work correctly. Overlays were popular in the early days of PCs because programs sometimes found that 640 kilobytes was not always enough. And if you remember that microcomputers that predate the PC often had less than 100 kilobytes of memory, overlays made the difference between a program running or not running on a given computer. We've spoken about the addresses contained in instructions and the addresses used to fetch and store data, but we haven't given them names yet. The logical address is the address contained in instructions. These are almost always relocatable addresses. As we'll see shortly, they usually refer to some base address directly or indirectly, and usually use an offset or displacement, the number of bytes that our address occurs after this base address. By allowing the base address to change and referring to it indirectly, the exact location of instructions and operands can change as the program is loaded into different areas of memory without the program losing its ability to find its way. The physical address is the address used by the computer's hardware to locate data and instructions that it's fetching and the locations to which it will store data. Most relocatable addressing schemes involve storing a base address in a register and adding an offset to it. When a program is loaded into a different area of memory, the base register's contents are changed. Since the address of an operand will remain the same relative to the starting address of the program, the offset is still valid. By adding it to the new base address, the operand can be found time after time after time, despite the fact that its physical address will be different each time. On older systems, user programs were often as large as the memory that was available. There was only room for one process to be stored in memory at a time. For a system like this to handle more than one process, it needed to keep their memory images stored on disk, reloading them when the process became active again. The disk space on which they are stored is called backing store. Although most modern systems can store more than one process image in memory at a time, we will see soon that swapping is still used in memory management. Swapping processes becomes a little more complicated in this kind of scenario. First of all, we need the new process's image in real memory. And before we can load it into memory, we need to store the old process's image on backing store. After process 1's image is saved in backing store, we can now safely load process 2 into memory. This is in addition to all the other things that must be done to complete the process switch.